So it's actually vaporizing the filament at this point. That's insane. That's molten aluminum there. Holy cow. So this is another reason why you shouldn't leave your 3D printer running unattended. Hello and welcome to another episode of Nathan Builds Robots. Today we're going to be talking about hot ends. I previously made an episode about hot ends where I talked about melt zones, flow rates, and the heating and cooling requirements of a hot end. But a lot has changed in the 3D printing industry since then, and the hot ends are no exception. There's been some improvements that have been occurring over the past year or so, and I want to do an updated video to kind of talk about those changes. This includes the addition of ceramic heaters, CHT nozzles that are designed to increase your flow rates, and all sorts of other material and coating sciences that go into hot ends and nozzle design. One of the most significant changes is that most 3D printer companies are switching over to a ceramic style heating element. So let's take off the silicone sock on this Bambu Lab P1P and take a look at what that looks like. And you can see this little white piece. That's actually the heating element. It's held in place with this retaining clip, and if we just loosen that clip up, it's kind of caked into position due to the burnt and carbonized filament there. But if we loosen this up, you can separate this heating element. It's just a thin piece of ceramic with two wires leading to it. If we look at this Creality K1 hot end, we can see the same thing. It's a ceramic heater core hot end design. Now this one's a little bit crusty because in a case of blatant user error, I was printing this with a flow rate set to 150%, so it was massively over extruding until this hot end was ramming into this pile of, molten plastic that was being laid down, and it eventually broke and started leaking. So, whoopsie daisy. But we have a more pristine example of this K1 hot end here that we can take a look at. And as you can see, it's using the same whitish material. It's another ceramic hot end. This one is circular instead of flat, like on the Bambu Lab machine. Now the interesting thing about these circular heating elements that are now being used in 3D printers is that the only reason they became feasible to mass produce is due to the volume of e-cigarettes being built and sold. So these were actually designed to be installed in an e-cigarette, so that brought the cost per unit down to the point where 3D printer manufacturers were like, hey, we can use these in our printers. There are some unique challenges with integrating a circular heater element. These challenges were mostly avoided by Bambu Lab because they're just using a flat heater element, and that's probably a lot cheaper to manufacture. It might not provide as uniform of heating as a circular heater element, but it's pretty close. These ceramic heater elements are made out of a variably conductive material, so basically the resistance changes in response to temperature. This allows you to dump more power into these when they're cold, so during startup they're able to heat up faster. And if you get into a thermal runaway situation where the 3D printer is broken and just applying 24 volts to this thing constantly, it'll actually limit the power delivery. So it's simultaneously faster at heating up and safer when you get up to temperature. Now when you compare the ceramic heater elements to a traditional heater element, like this one, it's a little cartridge style heater, they're a little bit different in the way they handle thermal runaway. Let me show you what I mean here. So right here we have a Magician X2 from Mingda, which was sent to me for review. I didn't pay for this machine, but upon powering it up, I noticed a really big issue, and that's that it entered thermal runaway right away. So I turned the machine off. But in the sake of science, I'm going to turn this machine back on and see what happens during a thermal runaway with a cartridge-style heater element. Now, it's always important to be safe while you're doing these crazy experiments, so I have my fire extinguisher on hand. And remember, if you like what I do here and want to see more experiments like this, remember to like this video and subscribe to my channel so you can see more. Thermal runaway protection is great and all, but it only works if your firmware is functioning properly and is free of bugs and there's no other issues in your system. You can easily end up in a situation where there's a hardware or software failure that results in an uncontrolled thermal runaway. So in cases like that, you're always going to want to have some form of mechanical protection that's built into the system and is inherent, that's not reliant on software or electronics to work properly. For example, you could have a situation where as soon as you turn your printer on, the MOSFET that controls the heater element is broken, and it just applies 24 volts to that heater element at all times. Even if the firmware was able to detect this kind of an issue, it wouldn't be able to do anything about it because it can't turn the hot end off. It can try to stop the MOSFET, but since the MOSFET is broken, you can't. It's just like if you had a light switch in your house that was stuck on. If you try flipping it off, it's not going to do anything. So as you can see here, I just turned the machine on, and it's registering a temperature of 101 degrees on the hot end and 94 degrees on the heated bed. which is probably not the case because these seem to be at ambient temperature, and unless I'm in hell right now, I don't think it's that hot in here. It's probably about 21 degrees Celsius, about room temperature. These aren't reading properly. So I'm going to go ahead and turn the nozzle on, and we'll just set it to 180 degrees, you know, a nice, safe, lowish temperature, and we'll hit heat. So you can see it's heating up, it's applying power to this hot end, but the temperature isn't changing. So we're clearly in some kind of thermal runaway situation now. Let's zoom in here and see what happens. Oh yeah, that's getting hot. So it's not detecting the increase in temperature. So we basically don't have the feedback loop working as it should. Normally it detects the temperature and then changes how much power is being applied, but since it's constantly detecting a high temperature, it's just going to keep heating up. And you can see I can push filament through this hot end right now. Oh, okay. So it's saying here, print halted, please reset heating, failed, extruder 1. So it's got thermal runaway protection and it was able to stop itself because the firmware has been implemented properly and it's detecting there's some kind of error. But let's see what happens if it didn't know there was an issue. This produces an error code that requires me to restart the printer. So that's a pretty safe way to fail. But you can imagine a situation where that MOSFET failed and the printer is unable to stop the nozzle from being heated up. Or let's say I set the temperature to 100 degrees and it thinks everything is fine. Alright, so let's see, we've got the nozzle set to 100 degrees. I'm not sure if it's applying heat or not. Let's set the nozzle to 102 degrees. So it's going to think it's almost there, so it'll be applying heat, but it's never going to get there. So that kind of error might not be large enough for the printer to recognize there's a thermal runaway. And that's what I mean by it's always better to have a mechanical inherent failsafe instead of relying on software, because there could be situations where the software doesn't recognize the issue and it causes a really bad thermal runaway. Alright, I can start to see thermal distortion of the air coming off of this nozzle. And if I push the filament through, it's able to feed just fine. But let's see if it's able to detect a thermal runaway in this situation. I'm just going to put the microphone next to the hot end so you can hear it, because it's making some interesting noises. Whoa, this filament is starting to smoke. When I push it through, you can see all that smoke coming out, and the plastic is just super liquidy because it's being way overheated. It's just going to keep going up and up in temperature, and even though this machine has thermal runaway protection, it's unable to stop this. Now the brass is starting to become discolored from the temperature, so this thing's getting super hot. So let's just feed a little more filament in there. Oh my goodness! Whoa, that's cool! Oh man. So it's actually vaporizing the filament at this point. That's insane. Okay, we're going to put a stop to this because eventually this is going to get so hot that that heater block might melt and fall onto this pile of plastic and pose some real issues. So let's cancel this experiment. Oh my goodness. Oh man. Alright, so this is a pretty crazy experiment. I kind of want to keep it going though, so let's let it keep going for a little while and see what happens as this temperature just keeps going up. So at this point you can see the heater cartridge is starting to turn red. I'm going to turn the lights off so you can see it change colors. And I'm actually going to get my ventilation set up. I'm going to leave this going here, and I'm going to get my fan plugged in because, oh my goodness, do you see that? The heater cartridge is going to fall out. It's melting the aluminum. Ugh, that's scary. Now I'm going to take an Allen wrench and just kind of poke it and see what happens. Oh my gosh, that's liquid. That's molten aluminum there. Holy cow. If this was printing, it would be sweeping this molten pile of aluminum back and forth and possibly dropping it on some stuff. So this is incredibly dangerous. I don't know if I would buy one of these Mingda Magician X2s because this is a little bit problematic. So I'm going to go ahead and stop this experiment and ventilate the room because this is out of control. This is just completely unacceptable. So yeah, that's pretty insane. That's like absolutely ridiculous. Oh man. Now that molten pile of aluminum has fallen onto this little thing, and yeah, this is like worst case scenario. So this is another reason why you shouldn't leave your 3D printer running unattended. I mean, as if you needed another reason. And remember everyone, this printer has a properly implemented thermal runaway protection, but due to the unique failure of this hardware, it's unable to stop itself because it doesn't recognize there's a problem. So I think it's time to cancel this experiment. I'm going to turn the power off. We'll turn the lights back on and get this room ventilated. Fortunately, I have this fan from V0, which I'm going to use to ventilate out the room. I'm going to put the microphone in the fan so you can hear how powerful this thing is. I was blowing this backwards the whole time. Well, that was exciting. But I think the moral of the story here is that 3D printer manufacturers should be moving towards designs that are inherently safe. Ones that can't melt down and drop molten 1000-degree metal onto your plastic parts and potentially start a fire. You saw the huge amount of fumes and soot being generated by that plastic. If there was an ignition source, that whole thing would have went up in flames. Something like this Bamboo Lab Hotend is inherently safer because with a PTC heating element like this, as it gets hotter, the resistance goes up, which naturally limits the current and reduces the amount of power delivered. Additionally, this Hotend is made out of copper and stainless steel, which have a much higher melting point than aluminum. So even at those elevated temperatures, this should hold together and not drop a pool of molten liquid metal onto your printed parts. And the other moral of the story is even with a properly tuned thermal runaway detection sensor, you still might end up in situations where that thermal runaway gets tricked or there's some kind of an electrical or mechanical failure that causes the power to be continually delivered to the Hotend. So you want something that's inherently fail-safe like this, and I really hope that 3D printer companies start taking safety more seriously and use those considerations in their design process to make everybody safer. Now this issue of thermal runaway and overheating is an issue on heated beds as well. Most heated beds are about 250 watts or 225 watts. That's your standard Ender 3 style heated bed that's running off of 24 volts. Those are fail-safe in the sense that if the power gets stuck on, it'll plateau around 90 to 110 degrees Celsius and it won't get any hotter than that. So even if there's a mechanical, electrical, or software failure where they continually deliver power to those parts, it should be safe. Machines like the Bamboo Lab P1P, X1C, and P1S, as well as the Artillery Sidewinder X2 and Creality K1 Max, are using an AC heated bed. So instead of running DC through the bed from the power supply, it's running electricity directly from the wall through that heated bed. And there's a couple hazards involved there, including dealing with higher voltages, but the main issue there is higher power. Especially if you live in a country with 230 volts on your electrical grid, that'll be delivering 4 times the power to your heated bed than your counterparts in 115 volt countries. So even if they tuned this bed to be perfectly safe on 115 volts, if you take this across the border into, I don't know what Canada's using, but if you're in Europe or Asia and you're running 230 volts, then that's going to be delivering 4 times as much power, which means you do have a major overheating potential. That's why on this Bamboo Lab machine, inside of the base of this plastic cover, there's a thermistor switch or thermistor relay. Basically, when it reaches a certain temperature, it's got a bimetallic lever that automatically flips due to the unequal thermal expansion of the two metals of the lever, and it just flips and opens the circuit and prevents more power from being delivered into the heated bed. And that will naturally limit it to, I forget what the number is, but it's somewhere between 120 and 160 degrees Celsius. So that will prevent your fire hazard. Now, mechanical parts like that still can fail due to corrosion or extensive aging or physical damage, but in my experience, that kind of failure is much less likely than an electrical or software failure, and you also have the electrical and software failures that are overlapping on top of that mechanical and inherent safety. So really, to produce a truly safe design, you want to have multiple factors coming together to basically try and stop it at multiple phases, and you'd need all the systems to fail in order to not catch a fault. Statistically, you're multiplying the probability of failure of those two events together. So let's say you had a 1% chance of any given printer having a failure of that sort. Well, if you have two systems that each have a 1% chance of failure, you multiply them together and you get a 0.01% chance of failure, which is much safer. And it's just a matter of how much do you value safety. Is it okay to occasionally have printers drop molten metal onto flammable plastic parts? I'd say it's not. And I'd feel much more comfortable running a design that's 2 orders of magnitude safer. Now, I'm not going to go through and prove that on this Hotend, because I just finished cleaning up the air here. But basically, if I were to apply 24 volts to this Hotend, the heat would just naturally be dissipated into this block, and it would never get hot enough to glow. Now, if you've watched Nero 3D's video, where he had it kind of hanging off to the side like this, and running with its thermal runaway not triggering properly, or at least waiting several minutes before it triggers, this heater will get red hot. But if it's dissipating its heat into this heater block, that increased surface area should reduce the temperature that gets to, and it should be much safer. However, it's still not a good situation to be in, and it should be avoided whenever possible. And when all is said and done, it's always better to have a human in the loop, so someone that can watch these machines and see if anything's getting out of hand and manually stop them. So this is a public service announcement to never leave your 3D printer running unattended. There's all sorts of bad stuff that can happen, and you don't want to burn your house down just because you wanted to get a project done a day sooner. Put safety and security measures in place in order to protect yourself. You can have stuff like smoke alarms and fire suppression systems, or just put your printers in a non-flammable area with nothing nearby that could be an ignition source. So there's a lot you can do to protect yourself, but yeah, you should really be taking it seriously. To improve heat transfer between the heating element and the heater block, they use some sort of thermal compound. On the K1 Hotend, they're using this grayish thermal compound, and they're using something similar on this Bamboo Lab Hotend. Thermal compound like this just improves the overall performance of the system. I myself have a gigantic jug of boron nitride paste that I apply to my Hotends between the heater element and the heater block, between the nozzle and the heater block, and just all over the place just to improve the thermal performance. Reducing the interface resistance between the heating element and the heater block lets you heat up the heater block faster and gives you more precise control over the temperature of the Hotend, which ultimately improves print quality and consistency. If you have fluctuations in the temperature, that's going to affect the viscosity of your printed plastic, and overheating or underheating of your polymer could also cause performance issues for the materials that you're printing. If it's printed too cold, you might have bad layer adhesion. If it's printed too hot, you might be breaking down the polymers and making the material weaker. Add to that, when you overheat your plastics, they release more volatile organic compounds and microparticles. So having good, consistent control over the temperature of your Hotend is important. The nonlinearity of this heater element might pose some problems in controlling the temperature. It's roughly linear in the areas that you're going to be operating in, and you can tune it for the temperatures that you print at most often, so it's not too big of a deal. When compared to traditional cartridge-style heater elements, I think the pros outweigh the cons here. One of the advantages of using a ceramic heater element and using a more compact Hotend design is that you reduce the thermal mass of your Hotend, which means you can heat up and cool off faster. And sometimes you'll have to wait for the print head to cool off before it moves on to another step of the print. Having that low thermal mass is really beneficial here. And that's something I think Bamboo Lab have done a great job of. If you take a look at this heater block, it's super small and lightweight, which helps with print speed because, it's easier to accelerate this back and forth, but it also helps you change temperatures of the hot end more rapidly in response to changing environmental conditions or at the end of a print when you want everything to cool off so you can turn the fans off. There's also advantages to having increased thermal mass, the main one being that you can hold the temperature more consistently, but I think having a lighter weight and more responsive hot end is better for print quality overall. We've also seen improvements in nozzle technology from companies like Slice Engineering, Bond Tech, Bamboo Lab, Diamondback, and Creality. I'm going to go ahead and unplug this printer and get it out of the way here. With regard to nozzles, the prevailing wisdom has been if you want higher flow rates, just make the melting chamber longer. So you ended up with the volcano nozzle, then the super volcano nozzle, and then just like really long stuff just to be able to melt plastic at ever-increasing flow rates. But starting with Bondtech's introduction of the CHT nozzle, they added some channels in there to split up the flow of the plastic, which increased the surface area and the rate of shear and the amount of mixing that occurs in the hot end. And basically they were able to increase flow rates without making the melt chamber any longer. So now achieving high flow is more of a multifaceted approach where you have to optimize the materials, the geometry of the nozzle, as well as the melt zone length. So now there's a lot more room for optimization and ways to improve your 3D printer speed without just making the melt zone as big as possible. Although that certainly still is a popular approach. Another practice that's becoming increasingly common is to use a bimetallic nozzle. The first type of bimetallic nozzle I used was this one from Phaetus. It's a copper nozzle with a tungsten carbide insert, which is designed to have high thermal conductivity and abrasion resistance all wrapped into one nozzle. But this has started to become increasingly common to the point where some nozzles are shipping stock with bimetallic nozzles, like this one from the Creality K1 Max. You can see it's got a hardened steel insert pressed inside of a copper body. It's also using a bimetallic heat break, which was first popularized by Slice Engineering. Some other innovations that we've seen is the use of more advanced material coatings. This right here is a Gamma Master nozzle from Slice Engineering, and they claim it has an abrasion-resistant, low surface energy coating applied to the nozzle, which helps make it slicker so that plastic doesn't adhere to it. The main reason you'd want to upgrade to a nozzle with a better material finish that's less sticky is because when you're printing materials like PETG, they really tend to stick to the nozzle. Just take a look at this nozzle that I was using on my Bamboo Lab P1P. You can see the PETG has really stuck on there and kind of made a mess of it. By using a less sticky coating, you'll get cleaner prints and have less issues with blobs of material getting dragged around, causing print failures and artifacts that are just unsightly. And those harder, more abrasion-resistant materials are going to help you print things like carbon fiber reinforced nylon or glass reinforced ABS. Basically, anytime you're going to be adding a hard material into the mixture of your filament, a hardened nozzle will be necessary. Otherwise, it'll slowly get abraded, which will change your nozzle geometry, and eventually you'll start getting failed prints or just lower quality prints. Additionally, you have nozzles like this one from Bondtech, and sorry Bondtech, I don't have a more pristine example of one of your nozzles, but this is a CHT nozzle, and you can see it's got some plastic built up on here, but even on this nozzle that looks like it's been through some stuff, you can see the plastic isn't sticking to the tip of the nozzle. And that's probably due to them using an ultra-smooth, adhesion-resistant surface finish on those parts. When I peel the plastic off of the back there, you can see that three-lobed design that helps split up the plastic and helps them increase heat transfer into that plastic. Now this is a bimetallic CHT nozzle, so it's got some kind of hardened material inserted into the center, and it has that flow-splitting die. So altogether, this is giving you better flow rates as well as abrasion resistance. One of the motivating factors for hot ends with higher flow rates are the high-speed printers that we now have access to. So since this tool head can move around so fast on my P1P, as well as on my fully enclosed P1S down here, you're going to need to increase those flow rates in order to keep up with the high speed of that print head. With all other factors being the same, the faster you move the print head, the more plastic you're going to have to lay down. So there's just a lot of improvements and development that's happening in the nozzle space. One of my favorite examples is this Bamboo Lab hot end. Now, I don't have data on how much it costs them to manufacture these parts. That kind of information is usually held secret by companies. But to me, it looks like a very low-cost nozzle, thanks to some clever manufacturing techniques that they've used. So for the Hotend heatsink, that's made out of an extruded piece of aluminum. When referencing the old school type of heater block, that was made out of a chunk of aluminum with several holes drilled and tapped into it. The heat sinks were often machined out of metal, and machining metal is always a more expensive process that you try to avoid whenever possible. By extruding this heat sink out of aluminum, they're able to make those very inexpensively. That's one of the cheapest ways to form aluminum. And they've done some post-processing machining to add some extra features onto this part. But the bulk of the material is being formed in an aluminum extrusion process. Then they're just using press fits to assemble everything together. So they press a steel tube into the heatsink, then they press this small copper heater block onto that steel tube, and they press this nozzle insert into that heater block. So altogether, that's got to be a very low cost of assembly and manufacturing, and they're also using less material and having less machining waste. Generally, when you produce more chips, that's going to be kind of wasted money because you're starting with aluminum that you're just ending up machining away and having to recycle. An added advantage of this press-fit nozzle construction is that it eliminates some of the common points of failure on a nozzle that is held together with threads. Just take a look at this nozzle that developed a leak. It produced a giant blob, and that blob can damage parts of the printer, including the hot end and any breakout boards or PCBs that are on the hot end. And it can cause wires to get torn out and just cause a mess in general. Anything that you can do to reduce the likelihood of failure, like using press-fit joints that could be more reliable, that could potentially increase the reliability of your subsystems, offering you a more reliable and stress-free printing experience. Anyone who's experienced the blob of death phenomenon that's caused by a nozzle leak like this is going to cringe a little bit just at the thought of that happening to their 3D printer. That said, even this press-fit construction can have issues. It looks like I have a leak there. You can see how some plastic is kind of seeping up to where it would be underneath that silicone sock. I'm not sure exactly what was going on there, but something like this still can develop a leak. They still need to follow quality control procedures and try and prevent that from happening. It's not foolproof, but it certainly seems like an easier way to connect parts together in a leak-proof manner. Now, there are leak-proof thread profiles, but these are not leak-proof thread profiles. These are straight cut in applications with hydraulic and pneumatic actuators, as well as in water cooling systems. They use what's called an NPT thread, which is a tapered thread profile, which is self-sealing. As you tighten it down, it makes a really good seal. These types of things don't seal very well because you have to have a clearance between the internal thread and the external thread, so there's always going to be a flow path to get through all of that stuff. Often with setups like this, you're relying on the flat portion of the nozzle at the very back to be butted up against the flat portion of the heat break, and that's supposed to fit together and prevent a leak. But that's not always reliable, as we can see here. If you look at a couple of other noteworthy heat sinks, this is the heat sink from the Anycubic M5C that I recently disassembled to kind of look at what's going on in there. And it's very nice. You can see that it's made using an aluminum extrusion as well. And we have this heat sink from Creality, which I don't know what's going on here. It's a very interesting design, but it looks like it starts as a small block of aluminum that they machine on a lathe in a process that's probably somewhat expensive. When you compare that to the Bambu Lab solution, that looks like a really low-cost, lightweight design. Also, since Bambu Lab is using these inexpensive flat ceramic heaters, they're probably saving a good bit of money there as well. While Bambu Lab's current line of nozzle offerings is pretty basic, they should be coming out with some new nozzles in the future, which include some high flow rate options and various different tips installed on those nozzles. And this kind of plays into their business model. I mean, you have to buy these kind of specialized replacement nozzles from Bambu Lab, which is helping them continue to make money off of their customers and provide them with a level of support that only a closed ecosystem can offer. In addition to cooling fans, we've also seen some setups that use water cooling to keep the hot end heatsink cool. But I don't have any systems like that because I think it's a little bit overcomplicated for what you need. Unless you're dealing with super high ambient temperatures, like you're printing in a very hot enclosure, then you're probably not going to need a water cooling system, and something that's air-cooled like this will probably be just fine. Hopefully this video has helped give you a better understanding of the design changes, material process advancements, and material science advancements that have helped improve nozzle and hot end technology on our 3D printers. What started out as a humble aluminum block with a couple of holes drilled into it has quickly evolved into a complex piece of engineering that uses multiple materials, coatings, and manufacturing processes to help give you the optimal experience when you're printing along. If you found this video helpful or educational, make sure to like it and subscribe to my channel so you catch more content like this. Alright, thanks for watching this episode, and I'll see you in the next one.